All right. Hello, everyone. As you just said, the title of this talk is Transductive Learning Equivalent to PAC Learning? This was joint work with Shaddin Dughmi and Yusuf Kalayci. So we're going to start out introducing the PAC learning setting. I guess you've already heard the PAC learning setting a couple times today, so I'll go through this pretty quickly. In the PAC learning setting, you have some distribution, you have a training set, which is sampled from that distribution, and the goal is to output some sort of a predictor, which is going to give you a high probability guarantee on future data points sampled from this distribution. In contrast to this setting, one can study the transductive learning setting. In the transductive learning setting, it's not quite like the PAC setting. We give a little bit and we take a little bit. The sample, so instead of a distribution, the adversary will give us a fully specified sample of n data points. Then we're going to choose a data point from this sample uniformly at random to be the test point. The remainder of the sample is going to be the training set. So we're going to try to train a learner on all of the data points except for the test point, test on the test point, and our goal is going to be to output a predictor which has low in-expectation error over the uniform selection of the test point. So we're giving up our high probability guarantee in exchange for an in-expectation guarantee, but we're giving the adversary a lot more power in that the adversary can now fully specify the sample that we're learning. So there are a few benefits to this model. First off, the optimal learners under this model are quite easy to describe. They have very simple and elegant descriptions. And also, this sort of turns learning into graph theory. There are a lot of really nice graph theoretic techniques that can allow us to analyze the learners that perform well in a transductive setting. And then this is and also a lot of recent work has connected transductive guarantees to PAC guarantees. A lot of interesting work in the PAC learning setting will use a transductive learner somewhere along the way in the analysis. And this setting works very, very generally, but you can imagine multi-class classification. We'll be talking about multi-class classification in this work. Okay, great. So at first glance, as I mentioned, the transductive and the PAC models might seem very, very different. However, we're going to ask the question in this work, are they equivalent in some strong sense? We're going to show that the answer is yes in many settings, and we're going to leave the question open in other settings. And a lot of literature has suggested that there's a pretty deep connection between these two models. So let's start out with the realizable setting, which has already been studied pretty heavily. So in the realizable setting, transductive multi-class learners, it is known that they can be converted to realizable PAC multi-class learners with only a little bit of loss in the samples. There's not a significant loss in the samples. This was shown in a recent paper by Adnan Ali et al. And also, there are folklore results reducing in the other direction, where you can take a realizable PAC multi-class learner and convert it to a realizable transductive multi-class learner. For example, you could see a paper by Asilis et al. In 2024. So combining these two results, we can say in sort of a strong sense that in the realizable setting, PAC learning and transductive learning are really equivalent. Now, our contribution is going to be to extend some of these results to the agnostic setting. We want to look at the agnostic setting and ask whether we can get similar results to the ones in the realizable setting. In order to do that, we're going to start out by taking multi-class agnostic transductive learners, and we're going to convert them to agnostic PAC learners. We're going to try to go in the other direction. We're going to try to take PAC learners to transductive learners, but we're unfortunately going to fail. We were not able to get the reduction in both directions. So what we're going to do is we're going to restrict our attention to the binary classification setting, and we're going to precisely characterize the agnostic one inclusion graph, the sample complexity of the agnostic one inclusion graph for binary classification. And that's going to allow us to show equivalence in the agnostic case in the specific setting of binary classification. So let's go through a quick roadmap of how this talk is going to proceed. We're going to start out talking about the agnostic setting. This is going to, in this setting, we're going to show that multi-class transductive learners can be converted to multi-class PAC learners. This is going to be via a reduction, which is very similar to the work of Adnan Ali et al. In 2023. And then we are going to characterize the agnostic sample complexity for transductive binary classification. and we're going to show that it's no worse than the PAC sample complexity. This is going to be, rather than via reduction, via structural arguments on the agnostic one-inclusion graph. We're going to conjecture that this second argument, which we only present in the binary classification setting, will hold more generally than the setting in which we've proved it. But we're going to leave that as open work. So intuitively, what is our algorithm going to do? So intuitively, we're going to start out with a learner A. We're going to do some sort of a reduction, which involves adding a few more samples to the training set. And the output is going to be some agnostic PAC learner A prime, which is going to give us a high probability guarantee. So we're going to take in a transductive learner. We're going to add a few more samples and run an algorithm on it. And that's going to produce a transductive learner, or sorry, that's going to produce a PAC learner A prime. So this technique, which again is very similar to one used by Adnan Ali et al. In 2023, we start out with our original sample S, which has n data points, and we're going to add some set of k additional data points on top of it, which we're going to call our aggregation set. We're going to take our data points from the original sample. We're going to add on, and we're going to use the first sample in the aggregation set as a test point. Then we're going to add the test point back into the original sample and train another predictor. We're going to keep on training predictors. This is going to give us a basket of k predictors, which we can then transform into one predictor using a small additional cross-validation set. This cross-validation set is going to allow us to go into each of the k predictors and determine which one is the best, and that will give us a high probability guarantee. So what do we have so far? Well, we've constructed a learner A prime such that the PAC sample complexity of A prime is no more than the transductive sample complexity of A plus a few additional samples, So this demonstrates that PAC learning is really not a lot harder than transductive learning. However, this is not super great on its own. If PAC learning is no harder than transductive learning, that's kind of no good if transductive learning is hard on its own. So now, we're not able to demonstrate that this M-transductive term is small in general, but we're going to look at the specific setting of binary classification and show that transductive error is not too large when we restrict our attention there. In order to do that, we're going to look at this transductive error, and we're going to characterize it precisely using structural arguments on the agnostic one-inclusion graph for binary classification. Okay, so we've talked about the one-inclusion graph a lot. What actually is a one-inclusion graph? Well, in the one-inclusion graph, we're going to study the transductive setting by taking each possible labeling of the vertices, and we're going to assign that to a label in a graph. Then we're going to draw an edge between two vertices exactly when those two labelings differ in exactly one label. If you recall the definition of the transductive setting, this is exactly, each edge corresponds to exactly the problem faced by our learner. Our learner gets all but one of the labels for a sample, and it must decide how to assign the last label. In that way, our learner is really given an edge, and it must choose a vertex. Therefore, to precisely specify the behavior of our learner, we need to orient each edge towards the vertex which that learner will choose, and specifying an orientation of the graph will give us precisely the behavior of the learner. We note that the out degree of a node is exactly the number of times when the learner misclassifies a sample. A learner misclassifies a sample whenever it's given an edge, and it classifies the incorrect, and it classifies in the incorrect direction. Therefore, the most misclassified node is going to be the node with the highest out degree. To that end, the one-inclusion graph is going to try to find an orientation which minimizes the maximum out degree in this graph. Okay, so now let's see how we can characterize the sample complexity of this algorithm. Well, using a variant of Hall's theorem, we can demonstrate that the sample complexity of learning in this situation is characterized precisely by the edge density of the maximum density subgraph in the OIG. This can also be extended to the agnostic setting. In the agnostic setting, the adversary is no longer restricted to giving us a sample which is no longer restricted to give us a labeling which is consistent with the hypothesis class. Therefore, we have to put the entire hypercube in the one inclusion graph. But now instead of being restricted to the hypothesis class, if the adversary gives us a labeling which is very far away from the hypothesis class, they have to give us some amount of credit. They have to. We get some sort of a penalty. We get some sort of a penalty term, which tells us that it's okay that we missed some of the samples. So we can orient this graph in a similar way, trying to minimize something like maximum out degree. But now it's going to be some sort of an adjusted out degree. It's going to be an adjusted out degree, where the adjusted term is going to be some sort of a distance term to the hypothesis class. So now the sample complexity of this algorithm, Asilis et al. Showed in 2024, is going to be characterized by some sort of an adjusted edge density, where the adjustment is based on the distance from the subgraph that we're looking at to the hypothesis class. Okay, so this is the characterization of learnability, or this is the characterization of the sample complexity in this case. Now we're going to show the work that we did, which will actually characterize this in a combinatorial way. It'll actually give us a precise characterization of this in terms of the VC dimension of the hypothesis class. First off, we showed that this quantity will only grow when we symmetrize the set U. If we take the set U and add in the flipped labels. So that means that the adversary will always want to find a set U which is as large as possible in the cube. It'll want to return the entire cube when it is finding this maximum adjusted density subgraph. Once we find this quantity at the whole cube, once we put this quantity on the whole cube, we're going to find an intimate connection with the Rademacher complexity of our hypothesis class. And then, using this connection with the Rademacher complexity of the hypothesis class, we'll use a variant of, we're going to use Dudley's chaining argument, which is going to show that which shows that the Rademacher complexity is bounded by some form of a VC dimension. And then that'll tell us that the transductive sample complexity will be given by the VC dimension of our hypothesis class divided by epsilon squared. Now, this leaves us with a natural open question. That is, do these techniques work beyond the setting of binary classification? There are two possible angles of attack, in our opinion, for this problem. First off, one might try to build a reduction in the other direction. We were unable to do that, but it's possible that we could convert PAC learners to transductive learners in a very general way. It'd be very nice if we could find a general technique for converting PAC learners into transductive learners. Alternatively, one could make structural arguments on the OIG. One could make structural arguments on the OIG where one could say that this argument that we described on the previous slide, maybe it also works for multi-class one inclusion graphs. If we could resolve this problem, then that would mean that in a very strong setting, PAC and transductive learning are really equivalent. So thank you for your time, and I hope to see you at the poster session.
Do you have time for a question or two?
So you said you couldn't bound PAC. Okay, so one of the directions doesn't work, and you said for multi-class, it doesn't work for multi-class, correct?
Correct?
Is that even for finite number of labels?
For finite number of labels, I guess for finite labels there is.
I think there should be equivalent for finite labels, right? Or?
Yeah, there's I don't know off the top of my head, but I guess for finite labels you could sort of show equivalence to the you could sort of turn it into binary classification. I believe you could do something. Yeah.
So the separation only occurs at infinite labels, right?
I believe so. I'm not. Yeah, I would need to make sure, but that sounds good.
You lose the log.
Use the log,
Yeah,
log K.
Yeah.
Makes sense.
Yeah. Thanks for a very nice talk. So one question is about the VC bound. Like, you use the bound in the transductive setting in terms of the VC dimension, right? Yeah. But is it just possible to directly bound the Rademacher complexity and get this VC bound, like without going through any one inclusion graphs here?
Let's see. Sorry. So you're saying directly bound the Rademacher complexity
of H, right? Or in the transductive, because whatever you have in the inductive case, you can just do the same chaining argument for transductive, like the concentration equalities remain essentially the same, and chaining should work, I think.
Interesting. Let's see. I would need to think about that as well. I believe that I would need to think about that as well. Let's see. So you're saying something like we take the hypothesis. So you're saying if we have
if we have a VC class, we have a transductive like setup. So we just prove the uniform convergence style result for the this sampling with replacement or whatever, and then the same VC will appear just for ERM. No?
It sounds a little bit more involved, so let's maybe take this one over the...
Yeah. Okay.